A very warm welcome to the wonderful world of chemistry. मैं हूं शिशिर मित्तल और व्यास सर्टिफिकेशन की ओर से मैं आपके पास एक बार फिर लेके आया हूं NCERT Solutions किसके एक बहुत ही खूबसूरत और बड़े इंपॉर्टेंट चैप्टर के जिसका नाम है कोऑर्डिनेशन कंपाउंड्स। 12th इनऑर्गेनिक का चैप्टर है और मुझे पूरी उम्मीद है कि आप इसका भरपूर फायदा उठाएंगे। क्यों? क्योंकि ये सिर्फ कोऑर्डिनेशन के NCERT के मामूली वीडियो सोल्यूशन ही नहीं है। इन क्वेश्चंस के बहाने से हमने पूरे कॉन्सेप्ट्स डिस्कस करने की कोशिश करी और कोशिश करिए कि जितना आपको इसके थ्रू मिल सके मिल जाए। आइए शुरू करते हैं। एक्सप्लेन द बॉन्डिंग इन कोऑर्डिनेशन कंपाउंड्स इन टर्म्स ऑफ वर्नर्स पोस्टुलेट्स। Now, Werner was the first extraordinary scientist, inorganic chemist, who actually explored and gave a very scientific and a fairly accurate theory for coordination compounds. So, his work is primary and pathbreaking. And how did he start? Actually, he did a lot of work, but then, as our NCERT mentions, a few ideas which he proposed and which he gave and which are useful are as follows. Werner talked about primary and secondary valencies. Why? Because before Werner, people used to talk about, just a concept of valency. Like, why should a substance form a bond? They said that they had to satisfy the valencies. That was the concept of valency. Now, if you have if you have something like potassium cyanide and if you have ferrous cyanide, these are the compounds in which valencies are already satisfied. So, if you put them together, would they react? Actually, they react to give you K4FeCN6, which is a new complex compound. And since they could not understand what is happening, they said this is a complex. Nowadays, we call this a coordination compound. So, the concept of valencies for attaining stabilities was seemingly at fault. And Werner upgraded and modified this by supposing or suggesting that there might be two types of valencies, primary and secondary. What are these? Just take a look. In coordination compounds, metals show two types of linkages, that is primary or secondary valencies. The primary valencies are normally ionizable and they are satisfied by counter ions, not just negative ions, counter ions. Counter ions means if the complex species has a positive charge, then negative ions. If it has a negative charge, then positive ion also. Like in this case, the coordination entity has a negative charge. So, that is satisfied by positively charged potassium ions. So, that is the primary valency. Now, what is secondary valency? Secondary valency is something which is non-ionizable. If I dissolve K4FeCN6 in water, it releases potassium ions, K plus ions, and it releases FeCN6 4 minus ions. So, they are in that sense primary valencies. But if you just look at the portion within the square brackets FeCN6 4 minus, you find that these valencies are not ionizable in the sense 6 cyanide ions will never leave ferrous ion. Ferrous and cyanide always are very strongly bonded and they stay together. So, that is why they said their secondary valencies are non-ionizable. Okay. And anything special? Yes. They are satisfied by neutral molecules or negative ions. Now, these neutral molecules or negative ions these days are called ligands. Werner did not use the term ligands, but he meant the same. The secondary valence is equal to the coordination number and it is fixed for a metal. Let me warn you, Werner himself did not use the term coordination number, but he just used the term secondary valency. And what Werner used to call secondary valency is now, after roughly 100 years, we now call this a coordination number. Fine. And that is fixed for a given metal ion. Yes, that becomes fixed for a given metal ion. The ions or groups bound by the secondary linkages to the metal have characteristic spatial arrangements corresponding to the different coordination number. What does that mean? Not just this, Werner also talked about the geometry of ions. Through various experiments, he could conclude that these secondary linkages, yes, these secondary groups or the so-called ligands nowadays that we call them, when they are linked to the metal atom or metal ion, they are arranged in the form of a very special geometry. And that geometry depends upon what is the number. Say for example, if coordination number is 6, the number of secondary valencies is 6, then the geometry is octahedral. So, that way, so this is the meaning of the fourth point, and these were the points suggested by Werner in his fundamental theory. Ferrous sulfate solution is mixed with ammonium sulfate solution in 1:1 molar ratio. Okay, it gives the test of ferrous ions, fine, but copper sulfate solution mixed with aqueous ammonia in 1:4 molar ratio does not give test of copper ion. Okay, explain. So, this is actually the difference between double salts and the complex salts. What happens? What happens is that when ferrous sulfate and ammonium sulfate are mixed in the ratio 1:1, they actually, if you evaporate water, you can get actually a single crystal of a double salt. And what is that salt? That is ferrous ammonium sulfate, FeSO4 dot NH4 whole twice SO4 dot 6H2O. This is what you would obtain. What is this? This is a double salt. Anything unique about double salt? Yes, many things unique about double salt. If you have a double salt here, double salt retains the entities, retains the properties of its individual salts. That means whatever were the tests given by ferrous ions or sulfate ions or ammonium ions separately, this double salt single-handedly would be able to give you test for each of these ions separately. It will not change, it will not show you new properties, and that is why it is called double salt. So what is a double salt? If two or more simple salts can crystallize together, and if they can form a single crystal containing both the salts, that means you have ferrous ions, ammonium ions as well as sulfate ions in a single crystal structure. That is called double salt, and the important property of double salt is that the individual property of ions remain unchanged in case there is a formation of double salt. Perfect. Let's look at the second half. If copper sulfate is mixed with ammonia in 1:4 ratio, you know what happens? Actually, something very interesting happens. You get tetramine copper sulfate. Now, this is actually a complex salt. Oh my God, what has happened? Copper ion has actually formed a complex with not 1, not 2, not 3, but actually 4 ammonia ions. And now this is the entire cationic entity. Is it copper ion anymore? No. Copper ions are now bonded with 4 different ammonia molecules. So it is a tetramine copper cation. The nature of cation has changed. It is a new cation. It is a complex cation. That is why we call it a coordination compound or a complex entity. And this definitely has properties different from copper ions as well as ammonia molecules. It has a new entity which has altogether new properties which may or may not be common with copper ions or ammonia ions, ammonia molecules individually. And that is why it is called a coordination compound or a complex compound. Complex compounds always have new and different properties from their individual constituents. That is the reason why this difference exists. Explain with 2 examples each of the following. Coordination entity. Now there are 6 or 7 terms. I am supposed to explain you each term and give you a couple of examples. What is coordination entity? Coordination entity is an entity or a group of atoms in which a central metal atom is attached to a set of ligands. What? The entity in which a central metal atom is attached to a set of ligands or lone pair donors is called a coordination entity. For example, you could have CuNH3 whole 4 2 plus. Is this a coordination entity? Yes. You could have NiCO4. Is it a coordination entity? Yes. Another different one. They are not same. They are different molecules. Or you could have FeCN6 4 minus. Is this a coordination entity? Indeed. The coordination entity, sometimes it is also called by another name, coordination sphere, may have positive, negative or zero charge. And it consists of a metal atom at least, which is attached to a set of lone pair donors or Lewis bases like ammonia or carbon monoxide or cyanide. That, my dear, is a coordination entity. Instead of 2, I've given you three examples. You can take any two you like. This is done. Now let's take the second one, ligand. What are ligands? Ligands are lone pair donors or Lewis bases. What are ligands? Ligands are Lewis bases or lone pair donors. Lewis bases which are attached to a central metal atom through coordinate covalent bonds. So, if I have nickel which has formed coordinate bonds with carbon monoxide, say for example, this is an example, a very classic example of a ligand. In this case, nickel is attached to 4 ligands, as you can see, 1, 2, 3 and 4. Nickel is the central metal atom and each carbon monoxide functions as what is called actually a ligand. So is carbon monoxide a ligand? Yes, very much so. Similarly, ammonia could be a ligand. Similarly, cyanide ions could be a ligand. Any lone pair for that matter, any lone pair donor. And who's a lone pair donor? Actually, if you have a lone pair, you can always donate it. So any entity with a lone pair, in potential, yes, it can function as a ligand. Second point. Now, we are done with these. What is coordination number? That also is very interesting. What is coordination number? The number of lone pairs or the number of electron pairs which are donated, or the number of ligands. Not really. A more accurate version would be this. The number of ligand atoms directly attached to a single central metal atom is called the coordination number of that metal atom. What? Let me say it again. The number of, like this is 1, 2, 3 and 4. The number of ligand atoms, directly attached to one central metal atom is called coordination number of that metal atom. Please note, coordination number is a number which is attached with a central metal atom. So, depending upon the number of ligand atoms which are directly connected to metal atom, you decide the coordination number. There are many approximate or wrong definitions also of coordination number. A very stupid definition is the number of ligands attached to metal atom is coordination number. Obviously not. Why? Just look at this. I have a lovely oxalate ion. And the loveliness of oxalate ion is that it possibly can donate not one, but 2 lone pairs to nickel. Say for example like this. Now if this is the only thing, what is the coordination number of nickel? It has only one ligand attached. But how many ligand atoms? 2 ligand atoms are directly attached. So the coordination number because of this attachment will be counted as 2, not 1. Although there is only one ligand, but there are 2 atoms directly connected. So coordination number will be 2 because of this. That is why I said the number of ligand atoms directly attached to metal atom, that is the coordination number, and that is something which you need to remember or not forget. Very important point of distinction, coordination number. Then we have something which is called as coordination polyhedron. Wow, what is that? Actually, the geometry around this central metal atom, that would be termed as coordination polyhedron. What does that mean? If you take a coordination sphere and you talk about the geometry around that coordination sphere or the polyhedron which would be drawn in case all the ligands are connected and they are assumed at the corners of a polyhedron, that is a coordination polyhedron. Metal atom must be the centroid and the ligand atoms must be the corners of the polyhedron. Like, say for example, if you have linear geometry, that's pretty simple. But in case you have tetrahedral geometry, for example, NiCO4 is tetrahedral. So coordination polyhedron around nickel atom in NiCO4 is tetrahedral. And again I repeat, this coordination polyhedron is an imaginary polyhedron which will be formed by joining all the ligands attached to a single given metal atom. And that metal atom should be present at the centroid of that polyhedron. If I have to give you a couple of examples, yes, I'll give you. Say for example, if you have FeCN6 4 minus, lovely, yes. This has octahedral polyhedron, because if you add, if you connect all the 6 cyanide ions, they actually are at the corners of an octahedron. On the other hand, if you take something which is simpler, like let's say take Zn CN4 2 minus. This is tetrahedral. Why? Because if cyanide ions are connected to each other, you would find that they are at the corners of a regular tetrahedron. Zinc ion being at the centroid of that tetrahedron. So these are, my dears, coordination polyhedra. Then they have asked homoleptic and heteroleptic. If all the ligands are identical, then the coordination compound is called homoleptic. Like if I have 6 ligands, all of them are cyanide, this is homoleptic. If I have 4 ligands and all of them are cyanide, it is again homoleptic. So 2 examples of homoleptic are also these. They are homoleptic complexes. What is heteroleptic? If more than 1 ligands are present within the same coordination compound, then that coordination compound, my dear, would be termed as a heteroleptic compound. Like, you could just write down anything practically and that would work out. Like, say if I have rhodium, and anything, something fancy I'm taking. Now you take PPH3, whole thrice, Cl, something of that kind. Now, if you have this, then there are 2 ligands, triphenyl phosphine and chloride. How is this? This is an example of a heteroleptic complex. If you want to keep it simple, well, Fe, NO, CN5, NO2 minus. This is sodium, this is nitroprusside ion, for example. It has 2 different ligands, NO and CN. So cyanide and nitrosodium cation actually. Now, together they make a heteroleptic complex. Why? Because all the ligands are not identical. That's why. These are the definitions with 2 examples each. What is meant by unidentate, didentate and ambidentate ligands? Oh my God. Give 2 examples of each. Denticity means the number of lone pairs which is donated by a given ligand to a single metal atom. Mark my words, if one ligand donates 1 lone pair to 1 metal atom, that would be a unidentate ligand. Okay, that's nice. For example, I'll give you the example like H2O. H2O is an example of unidentate ligand. Why? Because it donates only 1 lone pair. It does not donate more than that, and that too only to a single metal atom. If you have OH minus, OH minus also is a very beautiful example of a unidentate ligand. Why? Because although it has 3 lone pairs, but it can get attached. Yeah, it can donate only 1 lone pair to 1 metal atom. Please note, OH minus might be able to donate 1 more lone pair to somebody else. These donated lone pairs are through coordinate bonds. Coordinate bonds are sigma bonds, and if you have 1 metal atom attached to OH minus, there is only 1 sigma bond possible. You cannot have 2 coordinate bonds like this with the same metal atom. Even if there is M2 and the other lone pair is being donated to M2, still OH minus would be a unidentate ligand only. Why? What is the definition? the number of lone pairs donated by a given ligand to a single metal atom. People eat away to a single metal atom and then keep getting confused. I'm removing that point of confusion by giving you the exact definition. Single metal atom. Don't miss out on that. So this interaction would be counted in denticity and absolutely nothing else. So there you are. Got it? Absolutely got it. Bidentate is done. And ambidentate ligands. Oh my God, what are ambidentate ligands? Amphibians, both land and water, animals which can live both ways. Ambidentate, if a given ligand can donate a lone pair in more than one ways. What is more than one ways? Usually through two different atoms or more different atoms, and that ligand is called an ambidentate ligand. If a given ligand can donate a lone pair in more than one ways, then that ligand is said to be an ambidentate ligand. That is the definition. Give me an example. Well, I will give you example. Didentate, I'll write down examples, but let's finish ambidentate first. If you have cyanide ion, for example. Now, cyanide can get attached through carbon or through nitrogen. This is called cyanide. This is isocyanide. Old name, but nonetheless a name. So cyanide in that sense becomes an ambidentate ligand. Yes, very much. Anything else? Of course. A very famous case, you have NO2 minus. Now NO2 minus could actually donate the lone pair through oxygen. Yes. It could also donate the lone pair not through oxygen but through nitrogen. Yes. So NO2 minus also becomes ambidentate ligand. Why? It can be attached to a metal atom either through oxygen or through nitrogen. In more than one ways the lone pair can be donated. It is ambidentate. Yes, very much it is ambidentate. Done. What about didentate? Didentate, if two lone pairs can be donated by a single ligand to a one metal atom. I'm just covering the middle point, didentate ions, ligands. What is a didentate ligand? A ligand which can, yes, go ahead. The ligand which can donate exactly two lone pairs to one single metal atom would be termed as a didentate ligand. For example, ethylene diamine, very classic case, NH2. CH2, CH2, NH2. Beautiful molecule. Is it a didentate ligand? Very much. Why? Look at the way it donates lone pairs. 1 and 2. And both are donated to the same metal atom. Is this a didentate ligand? Indeed, this is a didentate ligand. Ethylene diamine, as people lovingly call it. Is there another example? Of course, there could be. Let us say another metal atom we have. And let's take a very famous and a very popular one, oxalate ion. The very lovely oxalate ion. They can donate a lone pair each. Oh my God, there are two lone pairs donated. Yes, by one oxalate ion. Indeed. So what is that? This is a didentate ligand. Indeed, they are two classic examples and very popular examples of didentate ligands. Let's begin with the first one. CO, H2O, CN, EN. Now, before that, I must tell you something, that there are neutral ligands. Neutral means they have zero charge, like En, like H2O, like ammonia. And they are anionic ligands like F minus, Cl minus, Br minus, I minus, Cn minus. All of these happen to possess -1 charge. Let me see which are the ones which I am using. I guess this is just the set I am using. So, first I have CO, H2O, Cn, En whole twice 2 plus. Fancy. Now, En is a neutral ligand. Please note. That means En has no charge. H2O has no charge. So if I'm trying to solve this, I'll say this has 0 charge, this has 0 charge, so 0 into 2 is also 0. Cyanide has -1. Cobalt we don't know, say X. So X plus 0 plus -1 plus 0 into 2. This is the total charge, and total charge is written up 2 plus, it is +2. So therefore, X comes out to be +3. Oh my God, that is simple. Of course, that is very simple, my boy or my dear. This is +3. Done? Done. Are you ready for part 2? Do this on your own. Quick, tell me. Look at part 2, which says COBr2En whole twice plus. I have written this here, right? Cobalt says Y. Each bromine is -1, and there are two bromines. And each En is 0, and I have two Ens. And the total is +1. Don't you forget, it's +1. What do I get? Y -1 is equal to 1. So Y is equal to 2. Oh wow. So I have cobalt as +2 in second question. Yes, the answer of second question is +2. This is short. Yes, so let's take third one. PtCl4 2-. Let us assume platinum is Z. Chlorine is -1, and there are 4 chlorines, and it totals up to -2. So Z is equal to 4 minus 2, which is 2. Oh wow. So platinum also is +2. Yeah, platinum also would be +2 here. What about K3FeCN6? Let's write it down, K3FeCN6. Potassium. I'm sure, hopefully you are aware that all alkali metals have +1 charge, and all alkaline earth metals always carry +2 charge whenever they form any compound. Lithium, sodium, potassium always have +1. So potassium is +1. And we have 3 potassiums. What about iron? I don't know iron. Let us say it is F. Oxidation number of iron is F. And then we have 6 cyanides, and each cyanide is -1. And there is no total charge here, it is 0. It is not to the power 0, the charge is 0. That's fine. You solve for F, it comes out to be +3. Wow. So oxidation number, indeed my dear, oxidation number of iron in K3FeCN6 is +3. That is your fourth answer, and the last remaining question, fifth part. Let us say Cr. In Cr, oxidation number is small r. You have 3 ammonias. Each has oxidation number 0. Your total charge is 0. Ammonia is neutral, that means total charge is 0. -1, yeah, +3 times -1, and total charge of course is 0. Therefore R comes out to be +3 again. Indeed. So chromium and iron both happen to be +3 in 4 and 5. Using IUPAC norms, write down the formulae for the following. Now that is one simple one. How do I write down the formula? Let's first read this. It says, and always when you're writing the formula, first of all, try metal. Metal is zincate 2. That means I'm supposed to write zinc, Zn. Zn would at least be there. And then I have tetra, 4 hydroxido. So I have OH 4 times. And please remember, zinc has been given as +2. If zinc is +2 and I have 4 times -1, so total charge, sorry, zinc is +2 and -1 for OH and 4 for OH minus ions, so total charge comes out to be -2. So this is tetrahydroxidozincate. Honestly, they should write the word iron also. This is an iron, and the formula for this anion would be this. This is the answer. To question number 1, yeah. Second, potassium tetrachloridopalladate. Palladate, it means palladium. What is the symbol for palladium? Pd. Always look at the coordination compound first. It is palladium, Pd. Tetrachlorido. So you have Cl4. Palladium is plus 2, yes. And there are 4 chlorines, each of them is minus 1. So total charge comes out to be minus 2. So tetrachlorido-palladate is PdCl4 minus 2. And then you have potassium. Fine. So this is minus 2 and then you have potassium. What do? We cross multiply like this. So you have K2 PdCl4. Wow. This is the answer? Yes. This is the answer to part 3. Simple enough? Yes, indeed. Oh, I'm sorry. This is part 2, not part 3. This is part 2. Yeah. Let's not give it wrong number. And then we take up part 3. Diamine dichlorido platinum. Fine. So first of all, we have platinum, yes. Diamine. Amine is ammonia and di means 2. And dichlorido, Cl2. And platinum is plus 2, yes. Ammonia is 0 and each Cl is minus 1. So plus 2 into 0 plus 2 into minus 1. Total charge is 0. Oh wow, so this is a neutral compound. Yes, it is a neutral compound. It is neither an anion nor a cation. Fascinating. This is third answer. Okay. We have 10. We are proceeding, don't you worry. Let's clean some space and go ahead for the next ones. Fourth. We are taking up the fourth one. Potassium, we'll look at potassium later. Tetracyanide, nickel 8. 8 weight is useless. Hai na? Nickel, I have nickel Ni. Tetracyanide, so we have Cn4. Nickel is plus 2 and you have 4 times minus 1. So total charge is minus 2. So the whole dirty thing is minus 2. Okay. And then you have potassium. What do? Well, as I say, cross multiply. So you have K2 NiCN4. Oh wow, is this the answer? Yes, indeed, this is the answer. What is this? Pentamine. My God, some drama. Pentamine. Nitrito O, cobalt 3. Fine, that's not a big deal. I have cobalt. I have pentamine. So, amine is NH3 and penta means 5. And then I have nitrito O. What is nitrito O? It is N. NO2 minus, which is connected through O. It is often written as ONO to indicate that this oxygen is connected to cobalt. So I have, and this is cobalt 3. Cobalt is plus 3, plus 5 times ammonia is 0, useless. ONO is minus 1. So what is the total charge? Plus 3 plus 0 minus 1. This is 2 plus. Oh my God, this is a cation. Yes. Pentamine, nitro, O, cobalt 3. And ideally, they should write the word ion. They are not supposed to just leave it like that. If it is a cation or an ion, then by IUPAC nomenclature, you are supposed to write down clearly the word ion also. This is the formula. 5. Is it 5? Yes, it's 5th. Half the job done. Now the second half. Let's take a look at 6th one now. Hexamine, cobalt 3 sulfate. We'll take a look at the metal atom. Cobalt. Fine, cobalt. Hexamine, that means 6 times ammonia. And cobalt 3. Now ammonia has 0 charge, this has plus 3. The overall charge comes out to be plus 3. And what about sulfate? Sulfate has charge minus 2. What do? Well, we cross multiply. Tang, tang. So we get cobalt NH3 whole 6 twice SO4 thrice. Wow, this is the answer to question number 6. Very much indeed. This is answer to question number 6. Now quickly, what about 7th? Watch. Potassium trioxalato chromate 3. Fine. So we have chromato, that means Cr. Oxalate is C2O4. Please remember chromium is +3. And each oxalate carries a charge of -2. I remember this, that this is the formula for oxalato. So -2 into 3. So this is total charge is -3. Tris oxalato cobaltate, yeah, chromate, sorry. And then we have potassium +1. Charges, cross multiply. So what do I get? I get the answer as K3 Cr C2O4 whole thrice. Wow. This is 7th, yes. And the 8th, hexamine platinum 4. Actually, this would be iron. We should write the word iron. Hexamine of platinum, and you have NH3 whole. Hexamine means 6 times. And this would carry a charge of +4 because platinum is +4 and ammonia carries no charge. So overall charge on the coordination sphere would be +4. It's an ion. Please note, IUPAC nomenclature is very clear. If you have an ion, then after the name, leave a space and the word ion should be clearly written. It is an error in this NCERT exercise that the word ion has been eaten away. It's not a good thing to do. But again, they behave like gods to us. Well, I mean, I've just put a note as per true science and I'm going ahead. They need to correct this if they're listening. Otherwise, who cares? 9th. What is 9th? Tetrabromido cuprate 2. This is also iron. Tetrabromido cuprate 2. Copper is +2. Each bromine is -1. There are 4. So 2 minus 4 is -2. The overall charge is -2. And this is iron. Last and the least, not the least, people say. I just said it for fun, being least one. Pentamine, fine. We'll start with cobalt. So we have cobalt 3, fine. Pentamine, NH3 whole 5. Nitrito N, that means they are binding through nitrogen. So we normally write it simply as NO2. It is +3, +5 into 0, -1 into 1. So total charge comes out to be +2. This is also iron actually. This is the formula. There we have the remaining 5 answers, all on board. Have fun. Using IUPAC norms, write the systematic names of the following. This is real fun. We have 9 questions and we're supposed to write down names. Let's start. How do we do this? First cation, then anion. First all the ligands. So this is going to be hexamine. Please note double M here. Hexamine, cobalt, no space. Hexamine, cobalt, how much? This is 0 charge, this is -1 into 3, so 0 minus 3. So cobalt has to be +3. So cobalt 3 chloride. You don't have to write trichloride. Ionic valencies, the number is not necessary. First one this was. Now the second one. Oh my God, this is going to be a long one. I'll write it on top here. I have to list out all the ligands. This is amine and 2. So this is diamine. Diamine. Oh my God. And then we have chlorido. So chlorido. And then we have, what is this? CH3NH2 is methylamine. Methylamine. And all these 2 and 1, 3 and 1, 4, all these ligands are attached to central metal atom, platinum. I'll write platinum. not platinate, no. 8 is going to be there if negative charge is present on coordination sphere. Now Cl is -1, so coordination sphere carries a charge +1, so it is simply platinum. What is the oxidation number? Well, 0, -1, 0. So if you have 0, -1, 0 and everything adds up to +1, that means platinum must have charge +2. +2 and then space, and then I write down chloride. How did you calculate? How did you calculate? Just maths. See, platinum is X, ammonias are 0, and then -1 is chlorine, and methylamine is 0, and the Cl is -1, and total charge is 0. So find out X. X comes out to be +2. And there we have it. A simple calculation. Third one. Titanium H2O, whole 6, 3+. This is simpler than we thought. This is hexa because of 6, aqua because of H2O, titanium, and what is the charge? 3. Then I don't have space here, so I am writing down, otherwise space, that means leave a gap and then write down the word ion. And please note, if you have a cation or an anion, you must clearly write down the word ion. You can't just simply leave it there. It is necessary. It is not depending on your discretion whether you write the word ion or not. You are supposed to mention that. Right? There we are. Fourth one. Well, looks longish. It is tetramine. So let us write down tetramine. Chlorido, and NO2 is nitrito-N. Cobalt 3, no, yeah, this is 3 chloride. How do you say it is 3? Calculate. Cobalt, say this is Y. Ammonia 4, 4, but they are 0. Plus chlorine is -1. Plus NO2 is -1, and this chlorine also is -1, total is 0. So Y comes out to be +3, cobalt is +3. Simply add up the charges of each individual and get the charge on the metal ion. Easy enough? Yes. Oh my God, this is just a repetition. Hexa, aqua, manganese 2 ion. What about this one? Tetrachlorido. Now the only beauty is nickel, not nickel, but the coordination sphere has a charge -2, negative charge. So nickel 8 ion, nickelate 2 ion. Nickel would have charge +2, +2 with -4 will give me an overall charge of -2, which makes perfect sense. I have attached a suffix 8. Why? Because the coordination sphere carries a negative charge. Okay. How about this one? No. We need this one. Hexa, amine, nickel 2 chloride. -1 into 2, -2 plus 0, so nickel has to be +2. Simple calculation. Eighth, my God, we have a bidentate ligand. So we will write down bis. No, it is not bis, it is tris, because there are 3. Tris. Why not di or tri? With big organic ligands, we write down bis, tris, etc. Ethylene, diamine, cobalt 3 ion. That's it? That's it, my dear. And last and the least, tetracarbonyl. CO is named as carbonyl. Please note, this is cobalt. Capital C, small o. Capital C, capital O is carbon monoxide. The ligand's name is carbonyl tetracarbonyl nickel. That's it. Simple? Yes, simple and beautiful. 9.8 says list various types of isomerisms possible for coordination compounds, giving an example of each. This is roughly half the chapter. We are attaching a PDF giving the answer. It's plain theory, dumb, nothing special. Watch the answer. How many geometrical isomers are possible for the following coordination entities? Well, Cr C2O4 whole thrice 3 minus and CO NH3 whole thrice Cl3. Now, you will find that if you have a bidentate ligand, then bidentate ligand can simply get attached to only adjacent locations or cis positions. So, if I have an octahedral complex like this, I am just trying to make that. I have chromium and then I have ligands here. One, two, three, four, five, 6. O, CO, COO, O, CO, COO, O, CO, CO. I have drawn a beautiful diagram showing the geometry. Is geometrical isomerism possible here? No. Everywhere you have O, all oxygens, all from oxalate. No geometrical isomerism is possible. GI is geometrical isomerism. What about this one? Whenever you have MA3B3, there are two possibilities. Facial or meridional. FAC or BUR? Yes. Oh my God, what are they? I'll just explain. Just be with me and keep your attention up. Now, if I look at facial and meridional, you might be doubting what exactly are facial and meridional. Let me explain. If I have octahedral geometry, let me just draw for you a molecule, in fact 2 molecules with octahedral geometries. Yes, and six coordination number. Now, say if I have Cl, Cl and Cl. And say if I have Cl, Cl and Cl, then I would be having ammonia, ammonia and ammonia at the remaining locations, of course. Yes. Now, the fun part is, you would find, if I join these 3 Cl groups, like this. Can you see that the plane which is joining these Cl groups, it is not passing through the center of molecule. It is not passing through the metal atom cobalt. Yeah. On the other hand, if I join these Cl atoms, I get a very different kind of a plane. And why is it different? Because, my dear, this is a plane which seems to pass very much across the central atom, through the central atom. That is dangerous. No, that is not dangerous, but that is a fact. They are not the same. Of course, they are not the same. What are they? Since it is just passing as a face, please note, if I just happen to draw other faces also, do you see, I would get something like an octahedron. Yeah. So, out of 8 faces of octahedron, if I join these 3 groups, Cl, 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 or in general, if I have any MA3B3 type of a molecule, if I just join 3 locations such that they are all cis to each other, this Cl and this Cl are cis, this and this are cis, this and this are cis. And if the line joining these 3 does not pass through the center of the metal atom, or does not pass through the metal atom, then this isomer is called, this geometrical isomer actually is called facial, in shortcut FAC isomer. And if the plane does pass through, if the plane joining the 3 ligands does pass through the metal, the central atom, then it is called meridional, in shortcut MER isomer. FAC or MER, facial or meridional? There you have it. So the answer to this question is 2. There are 2 geometrical isomers possible and we have drawn both of them. Now let's take a look at this very beautiful question which says, draw the structures of optical isomers of 1, 2 and 3. You have 3 different ligands here, complexes. One very notable thing is, see, just note the type of these complexes. This is MAB3 type. Yeah, you could actually call it, MAA3. Capital A I have used to indicate a bidentate ligand. Both are AA, not AB, which indicates a symmetric bidentate ligand because oxalatines, like both are similar. Now, what is both? See this. This is oxalate, right? These 2 halves, I've said this is A, this is A. So this is AA, both the ends. They are symmetric because this end is similar to this end. Had this been COO minus, had the other one been something different, I would have called it AB. But I have this MAA, this kind of a ligand. Charge is immaterial. I have 3 bidentate ligands. In second, I have 2 bidentate ligands, and in the third one, I have only 1 bidentate ligand. And they're asking me to draw the optical isomers. Wow. How should I do this? Let's begin. Actually, drawing 3 is the easiest because there's only one way to draw this. What is that? Let me present that for you. What are you trying to draw? I'm just drawing, a structure. And then this is chromium. Yes, chromium. Top and bottom, left, right, top and bottom, left, right, like this. We have oxalate C2O4, O, CO, COO, O, CO, COO, like this. And we have O, CO, COO. Lovely. This is one optically active isomer, very much. And the other one would be the mirror image. Oh wow, how would that be? Just we draw the mirror image. O, CO, COO, O, CO, COO, O, CO, COO. Just like this. This is it. Wow. What are these? These are the optically active isomers of 1. It has 2 enantiomers. You have 1 enantiomeric pair. Both of them are optically active, yes. And actually, if you see, they are nothing but mirror images of each other. Fabulous. Now take a look at the second one. The second one has 2 bidentate ligands, and you must be very careful that the monodentate ligands must always be cis to each other. They, at least the similar ligands, should never become trans. Otherwise, you will have a plane of symmetry and the molecule would not be optically active anymore. Like, I have PT, fine, and then I have 2 ENs, so NH2, CH2, CH2, NH2. NH2, CH2, CH2, NH2, like this. And then I have 2 Cls which are cis to each other. Wow. Do I have a mirror image? Yes. Cl and Cl. NH2, CH2, CH2, NH2. NH2, CH2, CH2, NH2, like this. This is the way I have drawn. Actually, these are ENs, ethylene diamines. Are they chiral? Yes. Are they optically active? Yes. And which are the optical isomers? My dear, these are the optical isomers, and if you care to see, they are enantiomers. They are non-superimposable mirror images. Now let's take a look at third one. It says central atom is chromium. We have two ammonias. Fine. And what else? We have only one EN. Not a difficult thing to do. What do? We just modify this just a little tiny bit, and we say this is chromium, fine, NH3, NH3. Ammonia should be cis and chromiums should be cis, NH3 and NH3. Just look at this. Wow, this is similar, kind of. The only thing is, you have to note that Cl, both the Cls should be cis and both the NH3 groups also should be cis to each other. As long as that persists, there would not be a problem at all. Like this. Again, this is the answer for third. And are they an enantiomeric pair? Yes, very much. Draw all the isomers, geometrical and optical, of 1, 2 and 3. Fanciful. Now we have to draw all geometrical and optical isomers, and let's begin with question number 1, part 1. COCl2 En hold twice. Now if you have two monodentate ligands, my dear, these two monodentate ligands could be cis or trans to each other. So let me start by drawing them. This is octahedral geometry, right? So this is what I am going to get. We have cobalt, and we have cobalt. Fascinating. What are you drawing? I am just drawing an octahedral structure and trying to put ligands on that. If Cl atoms are trans to each other and we have En like this, this is the way we draw this. This is 1, but then at the same time Cl atoms could very well be cis to each other also. So these Cls are trans. So 1 and 2 are geometrical isomers, very much. But 1 is achiral. It is not optically active, but 2 is optically active. So you find you have 2 and 3. 2 and 3 are actually non-superimposable mirror images like this. Wow. What are they? They are actually enantiomers. They are optical isomers. So 1 and 2 geometrical isomers, 2 and 3 optical isomers. And 1 and 3 also are geometrical only. Why? Because 1 is trans and 3 is cis. That's the way it is. If you take a look at the second part, now I have NH3, Cl and En hold twice. This, my dear, is very similar to what we have done, except that instead of writing 2 Cl, I just write down 1 Cl and 1 ammonia. Would that make any difference? Not really. Again, if this Cl and ammonia are trans to each other, I would get one geometrical isomer. If Cl and ammonia are cis to each other, I would get a different geometrical isomer. Just like part 1, I would get part 2. All you need to do is, in part 1, just erase 1 Cl and write down 1 ammonia. There is nothing new. It is just a repetition. I got 3 isomers here. I will again get 3 here. 1 and 2 are very, very similar. Third one looks a bit different. I have 2 ammonia, 2 Cl and 1 ethylene diamine. Oh my God. What do I do here? Ammonias could be cis or trans to each other. Cl minus could be cis or trans. En is a bidentate ligand, and I hope you remember that bidentate ligand binds only at a cis location. So let me try to figure out all that, what is possible. First, well, we have cobalt, which is lovely. We have En, and now cobalt and En. I mean, this much is fixed, fine. I could have, in the last one, ammonias which are trans to each other, and chloride ions, ligands which are cis. Or the opposite, ammonia which is cis and Cl, which is trans. Please note, the nature of locations is such that I just can't have everything trans. But could I have everything cis? Let me try. If Cl and Cl are cis to each other, and ammonia and the other ammonia are also cis to each other, is that possible? Yes, that is very much possible. That is very much there. Does this possess a plane of symmetry? Yes, the red square is a plane of symmetry. Why? Because top and bottom are same. Again, top and bottom same, so this is the plane of symmetry. Both of them are achiral. 1 and 2 are geometrical isomers of each other. What about 3? 1, 2 and 3 are geometrical isomers. Yes, because in this one pair ammonia is trans, the second pair Cls are cis. In this the opposite, one pair is trans, the other is cis, but in this case chlorides are trans and ammonia is cis. In the third case, both monodentate pairs, Cl is cis and ammonia is also cis. Right. Fascinating. So there are 3 different cases, but this is also chiral because this has no plane of symmetry. Oh my God, is that so? Try this out. Yes, very much. What do we do in that case? Well, in that case, we make a mirror image also. So this plus mirror image, whatever you draw. These ones. So 1, 2, 3 and 4. 3 and 4 are OIs. Instead of 3, you could write 4 also here. 1 is GI of 2. 1 and 2 are geometrical isomers. 2 and 3, 2 and 4, 1 and 3, 1 and 4 are also geometrical isomers. But 3 and 4 together, if you take them just together, they are nothing but optical isomers. So in total, we have 4 stereoisomers in third part. Write all the geometrical isomers of ting tang, and how many of these will exhibit optical isomerism? What is ting tang? It is PT. Now A, B, C, D. Something like this. 4 different monodentate ligands. Please note, platinum plus 2 and palladium plus 2 with D8 configurations, they would be simple planar. I mean, in each of these cases, let me solve this nicely and neatly for you. I think you will discover this. It contains platinum plus 2. Electronic configuration of platinum plus 2, if you see, it is 5D8. And it is a low spin complex. Why? Because second and third transition series, they always give you a low spin complex only. Coordination number is 4, so I just take 4, so DSP2. The hybridization in this case, my dears, is DSP2 and the associated geometry is square planar. And the moment geometry becomes square planar, now there is a problem. What? Since it is planar, that plane itself would be the plane of symmetry. Yes. So the question is, how many of these will exhibit optical isomerism? The answer is none of these will exhibit optical isomerism because every molecule is going to be a chiral or non-chiral. Fine. Second half is answered. None of them, 0 of them will exhibit optical isomerism. But how many geometrical isomers? Let's try. I mean, it is just going to be a square planar complex. So all I need to do is just to make squares and write down how many different permutations, combinations I actually get. Okay, that's cool. PT PT, PT. Now, if I write down A, do you see that these locations are cis, but the opposite location is trans? There are two cis locations with respect to A, but only one trans location. So, A, on trans location, I write down B or C or D. A, B, A, C or A, D. Fine. Similarly, if I find B, trans to B is A. Yeah. If it is AC, the remaining portion would be BD. I just dump BD here. I just dump CD here in any order, and I just dump AD to BC here. And let me start seeing. Now, on the translocation of A, I could have had B or C or D. Is that done? Yes, that is very neatly and clearly done. On translocation of B, I could have had A, I could have had D, I could have had C. B, C, D, only three options. All three are met. Trans to C, I could have D or A or B. Trans to C could be A or B or D. I already have it. Trans to D could be C or B or A. I have it. Is that it? That is it. A maximum I could have is three geometrical isomers. Instead of A, B, C, D, just write down A as ammonia, B as bromide, C as chloride, and D as pyridine. That's it. I have three geometrical isomers and zero optical isomers. That is the answer. Aqueous copper sulfate solution, blue in color, gives a green precipitate with aqueous potassium fluoride, and a bright green solution with aqueous potassium chloride. Explain. That's not very difficult to see. If you have copper sulfate aqueous here, that means you have Cu2 plus aqueous and SO4 2 minus aqueous, yes, and copper ions aqueous. Actually, this is Cu H2O whole 6 2 plus. This is blue in color. It is the aqua complex of copper which appears blue in color. Yes. If you add a lot of potassium fluoride, what happens? You get K2Cu F4 as a precipitate, which is a green complex, and it is apparently insoluble, so it precipitates out like this. Fine. If you have Cu H2O whole 6 2 plus, and if you have Cl minus, you get Cu Cl4 2 minus, which is yellow. This is yellow. This is blue, as you know this. So because of this reaction, these reactions, the color changes to either a green precipitate or green coloration. Now you may be suddenly shocked with this. You could say that you have just written CuCl4 2 minus is yellow. But at this place they are talking about bright green. If this is yellow, from where does the bright green color come? Actually, see, I have indicated in the first case there is a precipitate, so the reaction goes forward. In the second case there is an equilibrium. Please note. That means at equilibrium you also have some molecules of CuCl4 2 minus chloro complex and some molecules of aqua complex. And do you know that blue plus yellow, it produces which color? Of course it produces green color. Oh my God, is that the reason? Yes, that is the reason. Together, the mixture of both the aqua and the chlorido complex appears greenish in color, and this is the origin of that green color. What is the coordination entity formed when excess of aqueous potassium cyanide is added to an aqueous solution of copper sulfate? Why is it that no precipitate of copper sulfide is obtained when H2S is passed through the solution? Please note, cyanide has a desperate affinity for copper ions as well as ferrous and ferric ions. In this question, there is no mention of ferrospheric, so we'll just talk about copper ions. First, let us take a look. If you have potassium cyanide being added to copper sulfate, it's a very extraordinary reaction. Why? Copper in copper sulfate is present as +2. But when cyanide forms a complex with copper, cyanide absolutely loves copper in +1 state. So cyanide in this case plays a double role. It's playing a double game, yes. Cupric ions are reduced to cuprous ions. Oh my God. And then those copper +1 cations now undergo complexation with cyanide to give you CuCN4 3-. Oh my God. So there is a reduction, then a complexation, yes. And then what happens to cyanide ions? Are they just used for complexation? No. Cupric ions are reduced to cuprous. So cyanide gets oxidized to the most dangerous and poisonous gas, cyanogen. Wow, it's a genie or cyanogen, deadly one. This is what is happening. Of course, you could get K2SO4 as a time pass, no doubt. And if you want me to balance this really, I'll balance it for you. Let me write down clean things like K3CuCN4. That is cyanogen. They're just brackets, nothing else. Right? Let's balance that. Well, Cn- to cyanogen. If 2 cyanides are getting oxidized, 2 coppers must be getting reduced. So if this is 2, let me make this 2. And there are 2 sulfates, 6 and 2, 10 potassium, 10 KCN. This sounds pretty good. 8 into 10, yeah, this is balanced. Done. So the coordination entity formed is this, K3CuCN4. Because it is very stable, because the concentration of free copper ions in the solution is so negligible that when you pass H2S, although CuS is highly soluble in water, there is absolutely no precipitation of Cu2S or CuS simply because the concentration of free copper ions in the solution is very negligible. That is why no precipitation.